Okay, well, we're going to go ahead and get started. It is at the appointed time. We like to stay on schedule around here. So first of all, I want to welcome everyone to our webinar on process measurement basics. I'm going to go ahead and mute everybody to make sure that we don't have too much interference during the presentation. We will have a Q&A at the end. If you have questions, I will do my best to answer them. If we don't get to all of them, we'll write them down and get back to you on a individual basis after the presentation. We are going to be recording this presentation, and it will be available for download sometime later today. So with that, let's get started. So we're going to start off with what is a thermocouple. It is two pieces of dissimilar metals that create what's called a seebeck voltage. It's an effect that happens with any type of dissimilar metals. If you take two types of metal, put them together, you heat up one end, it will create a voltage on the other. What this seebeck voltage measures is can measure the temperature difference between the cold side of these wires and the hot side. So if we get 0 voltage, that means there is 0 temperature difference between the hot side and the cold side. Why is this important? Because we can take different types of thermocouples, different types of metals, A and B, and they create different voltages. They can also create wires or materials that can be more resistant or resilient to different types of environments. So there are many types of thermocouple types. Those types include K, J, T, E, N, etc. Even refractory composites for super high temperature measurements. And each of those types of thermocouples are based on what two materials, your metal A and your metal B, are, whether it be nickel chrome and nickel aluminum, iron, constantan, copper, platinum. The list goes on, and there are many types of thermocouple wires. The important thing to know is that there are two dissimilar metals or alloys, and that each type of thermocouple has a very distinct output voltage per temperature plot. And they are used for different applications. You can see type E here has a very steep plot, meaning that its millivoltage changes quite significantly over a certain temperature range, which gives it a little more accuracy. It's also used in cryogenics quite often. Type J produces a nice voltage change, although it has limited temperature applications. And because it's got iron in it, it can also oxidize and rust. Type K is kind of right in the middle. It has probably the widest use in the industry, in all industries. It's got chrome in it, which helps prevent corrosion. It also makes it harder to solder to, which we'll talk about in a little bit. But it is very inexpensive, fairly accurate, repeatable, and it tends to be the industry standard. These other types are available based on your industry or the application that they're being put into. They're used for many reasons, some of which are that they have different temperature sensitivity ranges. That's the slope of the millivoltage to temperature plot. The more sensitive it is, the greater the voltage difference, the higher the accuracy, typically. The lower the sensitivity, usually the greater the temperature range that it can measure. So those are considerations. They have different costs, right? If you have a thermocouple that's made out of platinum, it's going to be more expensive than one that contains nickel. Some of those platinum thermocouples are needed for super high temperatures, and the application has to justify the cost. and different conditions. As we talked about, type J has iron in it. It can oxidize and get consumed by an oxidizing process if you're in an oxidizing furnace, etc. So we want to make sure that the thermocouple type matches what kind of environment we're putting it into. If we have an acidic environment or an oxidizing environment, we need to look at our thermocouple alloys to make sure that they're resilient to that type of environment. And they need to be durable and long-lasting for the process that they're measuring. You can get very mechanically fragile thermocouples that can be accurate and be resilient to the chemistry of the environment, but they maybe are just too mechanically fragile to be used. So we need to make a balance between accuracy and durability and the environment that they're going to be used in. And then lastly, they have to match your data logger input. I've seen all too often where somebody will have thermocouples that are attached to a fixture, and they might be type J, and they plug them into a type K measurement device, not knowing that different types of thermocouples produce different voltages and will require the instrument to be either shifted gears into a type J or type K mode, or that they use the right thermocouple for their logger input. So with our loggers, our ECD M.O.L.Es, we're all type K all the time. So if you have a type J thermocouple, it simply won't work. We won't understand the voltages we're reading from it, and it will cause errors in your measurement. So the next big consideration is once we have a thermocouple, the wire selected, and maybe the wire size, we need to talk about its insulation. Oftentimes people will look at type K thermocouples are good for minus 200 to 1200 degrees C. Well, that's the wire itself. It's not the insulation material that isolates the wire and keeps them from shorting, which we'll find out is important. So what types of insulation materials are available? They're varied and wide, but Teflon is probably the most common. It's good to about 500 F, 260 degrees C, and it's used in lower temperature electronics, applications below 260 C, of course. It has high abrasion resistance and is probably the most durable material because it's flexible and abrasion resistant. They last for a really long time, and they can be used in a lot of different applications. The food industry likes them because you can clean them easily, right? The stuff doesn't stick to them if you have cake batter or dough. They're relatively inexpensive. If you go over 500 degrees F, the Teflon tends to liquefy, and it can cause electrical noise or shorts. It will affect your measurement readings. So if you have a process over 500 degrees, what do? We go to a fiberglass insulation. These are usually rated to about 482 C, 900 F. The glass material tends to break apart if it's flexed very much, so they aren't as durable as the Teflon. They do handle higher temperatures, which is nice, but they fray and they have some other issues. So if you are using a process that's under 500, definitely use PFA. Over 500, you can go to glass. Now, if you have some type of heavy-duty industrial application where you need more abrasion resistance at a higher temperature, you can put this glass thermocouple inside of a stainless steel overbraid. So the stainless steel overbraid protects it mechanically. It still will break down and shed this glass material if it gets flexed very often. So they still are a little more fragile. They don't last as long as Teflon, but it can give you very high abrasion resistance if your application is needed for that. And then we have these sheath thermocouples with Inconel and other exotic materials that are for very high temperatures. And we even go into some refractory composite type of thermocouples that are ceramic based and can be mechanically fragile as far as shock or flexation, but can handle very high temperatures continuously. So your insulation type is dependent on your application. You don't want to use an insulation type that's not required. because of cost. Each of these are progressively more expensive to use and can cause other process difficulties. So these Inconel sheath thermocouples aren't as flexible as a glass overbraid, etc. Wire gauge, why is it important? Part of that is response time. So 40 gauge for electronics profiling, it's 3/1000ths of an inch in diameter. They make a very small bead, so it fits into small places onto small components. It has a very low mass, so it responds very quickly. If you're doing, especially if you're doing a fast process like wave solder or selective, you need something that doesn't affect the mass and that responds in a very short amount of time. Typically, they're easier to attach with solder, and that's because when we solder thermocouples to a solder joint, we're actually encapsulating the bead and sticking it to the product. And a smaller bead means it's easier to encapsulate and capture. The downside is it's mechanically fragile. These are baby fine wires, and they are not as strong as a larger gauge wire. We use these for profiling BGAs and, like say, fast response or very quick processes. If you have, like say, selective solder, wave solder, where your entire process window may be 5 seconds, these will react very quickly. 36 gauge, these are 5/1000ths of an inch diameter wires. This is the industry standard for electronics profiling. They are low mass and fast response, not quite as fast as 40 gauge, but they're mechanically stronger and more flexible than the 40 gauge thermocouples because they will withstand the process. You can use them multiple times without them breaking. So the repeatability is a little better. And it's a better choice for electronics. Still appropriate for wave solder and selective for your fairly fast processes. And they can be used in long curing processes as well. And then we get up to 30 gauge. This is 10/1000ths of an inch wire diameter. This is the standard for baking industry and cooking. It's mechanically stronger than 36 gauge. Oftentimes the industrial ovens in baking or other curing applications are wider. You know, you might have an 8-foot wide oven. And so you need to run these wires longer distances. Because of that increased distance and weight, we need something that's mechanically stronger. Because of the extra mass or size of this diameter wire, it's slower to respond. It takes a little more time for it to change temperatures, and it's best used for longer, slower changing processes. So this is where baking industry, curing, things that don't require a fast response time, it's better for. And then we get in bigger than 24 gauge or 20/1000ths wire. It's used for industrial and heavy duty uses. It's mechanically strong. You can screw these thermocouples down with screws. They can be welded to different parts of machinery, and they're kind of almost semi-permanent placement. They're just more robust. They are slower to respond, so again, slower processes, more of a continuous use type of temperature measurement rather than trying to capture process changes instantaneously. I'm going to talk really quickly about repeatability. Part of repeatability is putting the thermocouple in the same spot every time or taking your temperature measurement from the same spot every time. And so there are different things that we can do that. We need to, if we put a thermocouple down on a circuit board, we should document where that was. And profiling software can help you do that to help you document, or you can use a spreadsheet or a pencil and paper. The important part is that if we want a repeatable process and we want to be able to do this in the future, we need to know where we put that thermocouple down and what we're actually measuring. The position on the board that we're measuring. Same with bread. We make special sensors for the baking industry. We want to make sure that we get the coldest spot in this loaf. And how do we do that repeatably? If we stick a thermocouple down into this loaf, it can float. It can be further down than we expect or further up than we expect. And so we want to make sure that we get the exact middle of the dough every time. And so we have a sensor that helps us do that repeatably. Our attachment method matters. So when we make something that we're going to use for repeatability, we need to make sure that the thermocouple attachment is going to survive for the number of runs we expect to use it for. There are test fixtures that we make and others there, or yourself, where you can fix thermocouples down to a test pallet so that you can get the same results every time. If you want to use a circuit board for that, that's fine. You need to make sure that the thermocouples stay down for the number of runs you expect to use it for. We don't want to be using a temporary attachment method like tape if we want to use this for 10 runs. And that's what pallets and fixtures are used for. They can be mechanically attached in a very secure way and give you repeatable results. And the other thing is, if we are measuring a process, we need to make sure that the process is stable before we jump to a measurement stability, or vice versa. If we find variation in our process, we have to make sure that it's not our measurement system that's introducing that variability. It may be if you make a fixture or some type of test vehicle that is, the thermocouples are attached correctly and you can deliver repeatable results, then your process may not be stable, or your oven may not be capable of producing a stable process. Most of the times, the inverse is true. Your heating system is capable. We're just not measuring it correctly with our products and or test fixtures. So we want to make sure that we build repeatability into our measurement system. So with that, what are the best ways to attach thermocouples? Well, in electronics manufacturing, high temp solder is the best way to attach a thermocouple. There are easier ways, but there aren't any better ways. It's typically done with SN10. This is 10% lead, or I'm sorry, 10% tin, 90% lead. So you have to control it inside of your electronics manufacturing environment to maintain your RoHS. There is a RoHS exemption for thermocouple attachments, specifically for these high temperature, high melting point solders. SN5, that's 5% tin, 95% lead, has a little higher melting point. So if you have a process that's a little hotter, SN5 is the way to go. Either one of these, if you can see these have 2% silver. The silver will help with the wetting of the thermocouple. So if you get SN5 or SN10, make sure you get a type that contains silver. Some do, some don't. So check with your supplier to see if you can get a silver bearing high temperature solder. The other choice, if you don't want to have any lead on your floor, is to go with an AU80. And AU is gold, of course, and we know the price of gold now is incredibly expensive. It has a melting point around 280 degrees, and it's $600 a meter. So you want to use it sparingly. You want to reclaim it if you can. We tested it. It actually works pretty good. It wets to the thermocouple fairly well and is functional. It's also very expensive. The process for doing this, attaching your thermocouple, is you take the thermocouple bead. This happens to be a 40 gauge thermocouple. The bead's fairly small. And again, we're going to wet the end of the bead with our SN5. We're going to wick up the old solder that's on the pad because we don't want to really mix this. If we've got a sack here, it's going to bring down the melting point of our SN5 here. So we bring up the old solder that was previously on the pad. We add flux, and I'll talk about this in a little bit, and add our SN5 to the TC. It will only wet to one side of the TC, typically, even with an aggressive flux. But that's fine. We just need it to stick to something so that we can attach it to the pad or terminal. And we tape it down. This is, we don't tape down the bead. We tape down the wire itself for strain relief, so the bead doesn't want to pull off when we attach it. We hit it with a soldering iron to melt everything together, maybe add a little bit more solder, and then you can see here the bead is encapsulated inside this solder ball. So we've wrapped it up in a blanket to hold it down. It may or may not wet completely, but what we're looking for is a thermally intimate connection with this pad so that we can measure that temperature. And this is what it looks like when you pull away from it. Here's the tape. It's just there for strain relief. Again, this is a 40 gauge wire, and these are incredibly small leads. The photography leaves a little bit to be desired there because it makes it look bigger. Here's the secret weapon for thermocouple attachment. If you haven't used it before, get some. You'll be amazed at how much it helps to actually solder down thermocouples. It's Johnson's J35 soldering flux for nickel. It is incredibly aggressive. You don't want to get this stuff on your hands. Wear gloves, wear safety goggles. Don't get it on your clothes because it'll eat through them. It is very aggressive, but for thermocouple attachment and soldering down thermocouples, there's nothing better on the market. Not a paid spokesman for them. We don't have any stock in their company. It's just a really good product. So we like to pass that along. There's some misconceptions about, we need to know where that thermocouple bead is in that solder ball. If it's not on the pad itself, this is representing the thermocouple bead, and this is the solder pad. If the bead's up here on the top of this solder ball, you're not getting a realistic temperature, and that's simply not true. The thermocouples going into this wad of solder make two thermocouple junctions, one right here and one right here, and you're effectively measuring the temperature of the entire mass of solder. So that piece of solder that you've soldered down to the board becomes the bead, the solder bead of the thermocouple, the electrical interface for it. And that's both okay. Where we have problems is where we have a short somewhere else on the thermocouple wire. So anywhere that those wires touch, whether it be at the connector or somewhere where insulation has been melted through or frayed, that's where the thermocouple junction will happen, and that's where it will read temperature. Is at where those wires are shorted. So oftentimes you'll see this right at the connector because they get twisted up, and you do a data run and it looks like you're measuring ambient temperature or the temperature inside the barrier, and that's because you are. The wires got twisted at the connector, and that's where it's reading the temperature from. So we want to make sure that our insulation's in good condition, that there's not shorts, that we don't twist these up. Sometimes you'll see these in a rat's nest, all wadded up and knots, and you just never know what temperature you're actually measuring. So keep your wires organized, keep them in good condition. And these are consumable. They're not intended to last forever. If your wires start getting frayed, throw them away and get new ones. There's just no reason to do that. So take care of your thermocouples or replace them. Again, soldering's the best way to do it. It's difficult to solder, but it is the best thermally intimate, mechanically strong, repeatable way to attach a thermocouple. What's next? We have glues and epoxies. They offer good repeatability and durability, meaning that they can last for multiple runs. It's fairly easy to apply. You can use some strain relief and you put a blob of glue or epoxy down. It may take curing time. There's some really good UV cure stuff that's instantaneous that'll last for 5 or 10 profiles, or some of the more high temperature SMT epoxies can take 24 hours, up to 24 hours to cure. The pro and the con can be that it's an insulator. So the more you put on there, the more it's going to mask or insulate the thermocouple from the actual heat that you're trying to measure. So you want to use the least amount possible to prevent that. And I said that this might be a pro or a benefit is that in certain applications like vapor phase, we actually want to insulate the thermocouple wire before it gets to the bead. Uh, and this is because these exposed wires, if this pink is supposed to be the vapor or the condensate that's transferring the heat into the component, well, it's transferring heat into these wires, and it's going down those wires and actually adding heat to this thermocouple or to this solder joint through its exposure. And so we want to limit that amount of heat that is being pushed into that joint so that we get a true measurement of this joint itself. So we can use that epoxy to not only attach the thermocouple, but to insulate the wires so that the condensate doesn't drive heat through the wires into that solder joint to give us a better temperature measurement. Tapes. Tapes are fast and they're easy, but not so good on the repeatability side. So it conforms to the TC. You can kind of see where the bead is through its shape. It does hold its shape, and you can't see through it. And the glue, the adhesive, and in this case we're talking silicone. If you go get the aluminum tape from Home Depot, it's got an acrylic adhesive, which is the worst thing that you could do. It gives up at 150 C kind of temperatures. The silicone adhesive gives up at around 220 C. And that's where, or softens, it doesn't give up. So right at the peak of your profile, the most important time, your time above liquidus kind of area, the adhesive around here softens. And so they have different methods to try to get around that. You know, window painting, where you put down a square and then you put another window pane around it to hold it down when it softens. The bottom line is it's good for one or two runs. If you get beyond that, the probability that this thermocouple is lifting away from the surface increases each time you run it. So that's why it's not as repeatable as the more mechanically affixed methods, using glues or epoxies or soldering. It is fast and convenient, and that's why it's used widely. But don't use it on a test fixture that you're going to do for machine repeatability. You can't run this, a dozen times and have it give you the same results. Kapton tape, it's even worse than aluminum. It doesn't conform to the shape of the thermocouple bead. It's great for strain relief, but air will get up underneath here and this thermocouple will lift very quickly. So use your Kapton for your strain relief to hold the wires down, not for holding the thermocouple beads down. BGAs are a special animal. They're definitely more difficult to profile. And the methodology used for these are that we pre-drill a hole through the BGA so that we can stick a thermocouple up through that hole and then epoxy it in place. And this takes time and diligence to make sure that the thermocouple bead is the right height and that it's going to be, touching the BGA ball as it's placed. Then you'd place the BGA down and then you'd run this through to get its temperature. The other option is if you have an existing via, you may be able to stick a very small 40 gauge thermocouple through it and get to that same area without having to drill and backfill. Less likely, but also a option. So now we're going to talk about thermal protection. The barrier that you select needs to match the process and application that you're running it through. And we have a variety of barriers. You can see that there's some bigger, some shinier, some have phase change heat sinks in them. So these are all tailored to the application that we're heating in. Just like with our thermocouple insulation. The thermocouple insulation, if it's only good to 500 degrees F, you don't want to put it in an 800 degree F process. Same here. Some of these barriers are rated to thousands of degrees for hours at a time. Others are rated for hundreds of degrees for minutes. So we need to choose our barrier based on not only the time and temperature, but the type of heat that we'll be using. So there's three types of heat transfer. There's conduction, where you're physically touching a hot plate to the product. There's convection. This is either through some intermediary medium air. It can be transferred through vapor, uh, etc., water. It's being transferred through an intermediary medium. And then there's radiation. And depending on the types of heat that you'll be experiencing is the type of barrier that we would utilize for that application. So in conduction, we want to minimize the surface area so that there's a smaller path to conduct that heat through. Convection, we need to just insulate and protect. And then radiation, we want to reflect as much off as we can so that the transmitted amount is minimized. So in IR firing furnaces for solar, they use a lot of IR heat, and we can protect at 700 degrees for 4 or 5 seconds by just reflecting all that away. We need almost no insulation. In vapor phase reflow, the moisture conveys the heat convectively about 10 times more efficiently than in air. So we need more insulation, or we need to prevent that contact with the condensate. And that's what this is trying to show, is this heat flow. The hot side, or the heat, will go through the conductor, whether it be air, the condensate, or direct connection, and it'll travel towards the cold object. And we want to minimize the surface area or make this conductor less effective by blocking it or slowing down that heat penetration. And this is where we talk about the care and feeding of our barriers. Very seldom do our barriers just reflect off the heat. It's not like a shield that will sit there indefinitely. What we do is we slow down that heat penetration so that we can protect our instrument for the duration of the process. If that's a 10-second process, that's much easier to do than a 10-hour process. So the longer the time, the more insulation we need so that we can slow down that heat penetration enough to survive the process. And once we're done with that process, we take our instrument out and we let the insulation get rid of all of its stored energy. Now, even though the heat might be turned off when we come out of our process, the heat is still traveling in and through our insulation, and will eventually make it to the inside of our barrier. Most of our barriers use some type of microporous silica, and its whole object is to give a very obscure, long path for the heat to travel through to get to the inside. Now, the amount of time it takes for this very circuitous path to go through is dependent on how thick this material is. So the longer the process, the thicker the material. Now, once the heat's been applied, we've made it, we survived through our process, all that heat is still trapped in the center of this insulation. It's made it halfway through, maybe 3/4 of the way through, and now the heat's turned off. That heat wants to come back out. And this is what happens too often, is that our barriers are not cooled between runs. They'll hit the outside with some compressed air, they'll set it on a concrete floor, and they'll get the outside cool, and then they'll run it through a second process. Well, this heat took 15 minutes to get, potentially half the process time to get to the center. It's going to take half the process time to make it back out again. So if you have a 5-minute reflow process or a 20-minute baking process, it's going to take half that process time for this heat that's stuck in the center to get back out to the outside, where it can be evacuated and not used and not absorbed, or till it gets back to 100% functionality. And what happens is, like I say, the outside gets cooled off, this heat that's trapped on the inside starts migrating out, and then they put it back in the process again. So that heat that was in the center, it's already got a head start, and more heat's being pushed in from the side, and then you can see it's traveling further and further through the insulation material, and then at the end of the process, that heat's made it all the way through to the inside of the barrier. So this is where we cook our instrument, and not have a very good day. So we want to make sure that, again, when we start our process and we finish it, we let all this heat that's trapped exit out of the barrier so that we're ready to do our next run. If you have a long process with a phase change material, it can be an hour or more to get this collected, absorbed heat exit out of the insulation material. If you have a 5-minute process, maybe this is only 2.5 minutes, 3 minutes to cool it down and get it ready for the next use. The goal is that we get all of the trapped energy out of the insulation before we do our next run. So with that, I'm going to go ahead and unmute everybody and we'll open it up to questions. Any questions? Anybody? You can type them in if you want to. I'll be looking at the chat. If you are not wanting to speak.
Hi, Mark. This is Rudy from Creation, Vancouver.
Yeah.
I have question for when you explain about the PGA. So some myth is you need to drill it just to the last pad before pick through the pad. Is that true, or is it what you mentioned is you drill it through it and then you just touching to the ball, or even you put it between the ball?
Well, so you can probably get away with either. The difference is subtle. Most people can't drill and not go through the pad, and you're really you want the temperature of that solder pad interface. So if you're on the top side of it or the bottom side of it, doesn't matter. It's easier to drill all the way through, and then you can see the thermocouple bead at the height of the board and then measure it that way. So I think it's just a practicality. Most people don't have the ability to do that hundredths of an inch difference between being at the bottom of the pad and the top of the pad.
Thank you, Mark.
Yeah, absolutely. And we've got a chat. Let me see what that is. It says a thermal barrier that sounds like it has liquid inside. Does this mean that it has reached the end of its life? So if you have a thermal barrier that's got a phase change heat sink, it may have what's called a saturated salt solution, and it should not sound like liquid at room temperature or at 25 degrees. So what happens with some salt-filled phase change materials is after a certain number of thermal cycles, they lose the ability to go from solid to a liquid effectively. So I would have that heat sink looked at and replaced. And that's one of the reasons we, if we replace the phase change material, we'll probably go with a paraffin-based phase change because it can change phases indefinitely. It never loses its ability. It doesn't have quite the heat absorption that the saturated salt does, but it does a very good job. It's very close. What else do we have here?
Hey,
And
Mark.
somebody's asking for email the presentation. We will absolutely do that. Go ahead.
This is Matthew. I have a similar question about LGAs. So we have a product, LGA chips on one side, and they pretty much cover that one side, and that's what we're interested in profiling. So I pre-drill the PCBs like you had mentioned, and stick the thermocouple down, usually kind of bend it at 90 degrees to make sure that it's touching the back side of that chip. You know, I know you talked about epoxies and high temperature solders being the way to go, the best. But with that particular where you're drilling a hole through and putting it on the back side of the chip, you know, without drilling a huge hole, I'm not sure that there's a good way to do that. I've always used the aluminum tape and then kind of window paint around it with Tyvek, or the to my mind.
Yeah,
The Kapton tape.
Yeah, in that case, like say if you're drilling a hole, if you bend your bead over, depending on the bead size, the goal is that you measure the solder interface temperature, right? Either the ball or the chip on the top side where the ball is going to be, or the pad where the ball is going to land.
Right.
And if you have a thermocouple bead that's exactly the size of your ball, you may not need anything in there at all. You just need strain release so it doesn't pull out. So when you backfill the epoxy in the hole, let me see if I can get to that slide here. All you're doing is not making a hole for heat to travel up through. So this is where we're using it as an insulator. So we want the epoxy to be the same thickness of the board, and so that and the bead itself doesn't need to be attached to anything. It needs to be close to it, and we don't want heat to come up from this direction up into this hole that we've drilled and artificially heat this.
Right. Right. I guess one of the things I've done, and maybe this is, be curious what your opinion on this is, but I've used a little bit of like Tim's material type putty in those holes to hold it in place and make sure that it transfers the heat from that pad to the thermocouple bead.
As long as we, like say, if you're using something that's not a thermally conductive to fill that hole, we're going to be okay. If you're using something that's thermally conductive, it's going to take heat coming from the bottom. So the circuit board material is an insulator. It slows down heat penetration. So you want to fill that hole with something that's as close to an equivalent as possible. You know, make the hole as small as you can, you know, the size of your thermocouple wire. And in this case, you may want to come up, I don't know if I can draw this. I'm going to stop recording at this point too.